Black hole cosmology is one of the most provocative and imaginative models in modern astrophysics, suggesting that our observable universe may itself be the interior of a black hole. First introduced in 1972 by Raj Pathria, the theory builds on the Schwarzschild solution of general relativity and compares it to the closed Friedmann-Lemaitre-Robertson-Walker metric. Instead of viewing black holes solely as cosmic endpoints, the model proposes they could serve as birthplaces of entirely new universes. In this view, the Big Bang might not have been a singular beginning, but rather the expansion that followed a gravitational collapse in a larger universe. The central idea is that matter collapsing into a black hole does not compress into an infinite singularity. Instead, at extremely high densities, mechanisms such as torsion or limiting curvature prevent endless collapse. The process halts at a finite density, producing a bounce that initiates rapid expansion. From the outside perspective, the black hole remains hidden behind its event horizon, but within it, a new universe unfolds, potentially with its own physical laws and parameters. This idea connects to Lee Smolin's theory of cosmological natural selection, where each black hole spawns a universe, and slight variations in constants determine which universes are more likely to produce further black holes. The implications are profound. If true, black holes would not only shape galaxies, but also seed an endless chain of universes, forming a vast multiverse. This approach could resolve puzzles like the horizon and flatness problems without invoking traditional inflationary models. Yet, challenges remain. Critics argue the theory is speculative, with no direct way to test whether black holes create new universes. Observational hints, such as possible universal rotation or cosmic microwave background anomalies, are intriguing, but far from conclusive. Despite these debates, black hole cosmology endures as a daring perspective that reshapes how we imagine origins and endings. Whether ultimately proven or not, it expands the frontier of cosmological thought, suggesting that within every collapse may lie the seed of creation. The holographic principle is one of the most revolutionary ideas in theoretical physics, suggesting that the universe we perceive as three-dimensional may actually be a projection of information encoded on a two-dimensional boundary. First proposed in 1993 by Gerard Hooft and later expanded by Leonard Susskind, the principle emerged from attempts to resolve puzzles in black hole physics, particularly the question of how information is preserved when matter falls into a black hole. Drawing on Jacob Bekenstein's earlier work on black hole entropy, which showed that the maximum information content of a region scales with its surface area rather than its volume, the principle reframes our understanding of space, information, and reality itself. At its heart, the holographic principle proposes that all of the data describing a volume of space is stored on its boundary, much like a hologram encodes a three-dimensional image onto a flat surface. This radical view found its most precise expression in Juan Maldacana's ADS/CFT correspondence, which demonstrated a mathematical duality between a gravitational theory in anti-de Sitter space and a conformal field theory defined on its boundary. Through this duality, aspects of quantum gravity became tractable, transforming string theory and high-energy physics. The implications of the holographic principle are staggering. If true, it means that the three-dimensional world of stars, galaxies, and life is a projection, an emergent phenomenon arising from a deeper two-dimensional structure. It bridges information theory, thermodynamics, and quantum mechanics, hinting that matter and energy are secondary to information itself. This concept even reaches into philosophy, raising questions about the nature of perception and reality. Despite its elegance, challenges remain. Some models, such as bags of gold solutions, appear to defy the principle's entropy limits, and experimental verification has proven elusive. Attempts to detect holographic noise in gravitational wave observatories have produced ambiguous results. Nonetheless, the principle continues to shape modern physics, inspiring research across quantum gravity, cosmology, and condensed matter. The holographic principle remains speculative yet profoundly influential. Whether ultimately proven, refined, or replaced, it reshapes how we imagine the universe, perhaps not as infinite space, but as a vast cosmic projection. The simulation hypothesis is a bold idea at the crossroads of philosophy, physics, and computer science, proposing that the reality we perceive may be an advanced artificial simulation. While the roots of this concept stretch back to ancient thought, from Plato's allegory of the cave to Zhuangzi's butterfly dream and the Indian philosophy of Maya, the modern form was articulated by philosopher Nick Bostrom in 2003. In his seminal paper, Are You Living in a Computer Simulation?, Bostrom introduced the simulation argument, sparking intense debate in both academia and popular culture. The core of the hypothesis rests on computationalism, the belief that consciousness could, in principle, emerge from sufficiently advanced information processing. Bostrom outlined a trilemma. Either civilizations never reach the technological capacity to create simulated realities, they choose not to, or if they do, simulated beings will vastly outnumber biological ones, making it statistically probable that we are among the simulated. This reasoning reframes the universe as a programmed environment, rather than a self-contained physical reality. The implications are profound. If correct, then galaxies, atoms, and even human thought are artificial constructs within a computational framework designed by post-human intelligences. The hypothesis challenges traditional boundaries between reality and illusion, providing unsettling resonance with science fiction works like The Matrix. Philosophically, it reopens age-old questions about perception, knowledge, and the reliability of experience, while scientifically it raises the possibility that physical laws may themselves be artifacts of coding. Criticism, however, is substantial. Some physicists argue the idea is unfalsifiable and thus unscientific. Others highlight the astronomical difficulty of simulating an entire universe with all its complexity. Skeptics also question whether digital constructs could ever truly achieve consciousness, or whether the hypothesis simply reframes classical skeptical doubts in modern language. Critics like Sabine Hossenfelder and George Ellis dismiss it as pseudoscience, while others see it as an entertaining but impractical thought experiment. Despite such doubts, the simulation hypothesis continues to influence philosophical discourse, scientific speculation, and cultural imagination. Whether one day proven, disproven, or reframed, it endures as a provocative reminder that the nature of reality may not be what it seems, and that humanity might inhabit an elaborate illusion. The multiverse theory is one of the most ambitious and controversial ideas in cosmology, suggesting that our universe is only one among countless others. While the notion of multiple worlds dates back to ancient Greek atomists like Democritus and later thinkers such as Giordano Bruno, the modern scientific framing emerged in the 20th century through quantum mechanics, cosmology, and string theory. Today, it stands at the crossroads of physics and philosophy, raising profound questions about existence and reality. At its core, the theory proposes that beyond the observable universe lies an ensemble of universes, each with distinct properties, physical laws, or histories. Max Tegmark classified multiverse concepts into 4 levels: extensions of our cosmic region, bubble universes with different constants, quantum branches from the many worlds interpretation, and the ultimate ensemble of all possible mathematical realities. Brian Greene expanded this with 9 varieties, from cyclic and brane universes to simulated and holographic models. Together, these frameworks aim to explain puzzles like cosmic inflation, quantum indeterminacy, and the apparent fine-tuning of conditions for life. The implications are staggering. If true, the multiverse undermines the idea of a unique cosmic story, suggesting instead that every possible outcome may exist somewhere. It offers a potential answer to the anthropic problem. We live in a universe capable of supporting life simply because countless others cannot. This perspective shifts humanity's place from central to incidental. Criticism remains strong. Figures like Paul Davies and George Ellis argue that the theory is unscientific because other universes may remain forever unobservable, making it unfalsifiable. Others contend it risks becoming metaphysics cloaked in science. Philosophers have also questioned whether infinite unseen worlds constitute an elegant solution or a needless violation of Occam's razor. Despite skepticism, the multiverse continues to inspire both scientific research and cultural imagination. Whether one day confirmed, reframed as philosophy, or dismissed as fantasy, it endures as one of the boldest attempts to grapple with the question, is our universe alone? The heat death of the universe, sometimes called the Big Freeze, is one of the most widely discussed scenarios for the ultimate fate of the cosmos. Rooted in the second law of thermodynamics, the idea was first articulated in the mid-19th century by Lord Kelvin, who extrapolated the inevitability of increasing entropy to the universe as a whole. Earlier inklings can be traced to the French astronomer Jean-Sylvain Bailly in the 18th century, but Kelvin's formalization connected the concept directly to physics, framing it as a universal law of decline. At its core, heat-death proposes that as entropy rises, the universe will eventually reach a state of thermodynamic equilibrium. In such a condition, all usable energy would be evenly distributed, leaving no temperature gradients to power physical processes. Stars would burn out, galaxies would fade, and even black holes would ultimately evaporate via Hawking radiation over unimaginable timescales. What remains would be a thin, cold, and inactive soup of photons and elementary particles, cosmic silence on a universal scale. The implications are profound. Unlike models such as the Big Crunch, which envisions a violent collapse, heat-death imagines a slow, inexorable fading of activity. It transforms the story of the universe into one of inevitable dissipation, raising existential questions about the permanence of life, intelligence, and even meaning in a cosmos destined for stillness. For some, it echoes philosophical traditions of impermanence. For others, it is a bleak vision of eternal decline. Yet the theory faces criticisms. Some physicists argue that applying thermodynamics to the entire universe is problematic, since entropy for a non-equilibrium system is not universally defined. Others note that gravity, with its tendency to form structure rather than dissipate it, complicates the picture. Alternative scenarios such as the Big Rip, cyclic models, or vacuum decay compete with heat-death as potential endings. Despite uncertainties, the concept continues to shape cosmology and popular imagination. From Isaac Asimov's The Last Question to modern debates in physics, heat-death endures as a haunting symbol of cosmic destiny. Whether it proves inevitable or is one day overturned, it forces humanity to grapple with the limits of time, energy, and existence itself. The Big Crunch is one of the most dramatic theories about the fate of the cosmos, envisioning the universe not ending in eternal expansion, but collapsing back into itself. The idea dates to 1922, when Russian physicist Alexander Friedmann, working from Einstein's equations of general relativity, proposed that the destiny of the universe depends on its overall density. If matter were abundant enough, gravity could eventually halt expansion and reverse it, pulling galaxies, stars, and space-time itself inward until everything converged in a catastrophic finale. The core of the hypothesis lies in the interplay between cosmic expansion and gravitational attraction. In this scenario, the scale factor of the universe would eventually shrink to zero, compressing all matter and energy into a singular state of infinite density, resembling the conditions of the Big Bang in reverse. As contraction accelerated, radiation would intensify, stars would ignite and collide, and temperatures would rise to unimaginable levels. At the final moment, space, time, and matter would collapse into an all-consuming singularity. Philosophically and scientifically, the Big Crunch offers an intriguing mirror image of creation, an end that could seed a new beginning. Some theorists extend the model into the Big Bounce, suggesting the universe may undergo endless cycles of expansion and collapse, a cosmic heartbeat without beginning or end. Compared to heat-death, which imagines fading stillness, the Big Crunch presents a fiery and dynamic conclusion. However, observations in the late 1990s complicated the model. Studies of distant supernovae and the cosmic microwave background revealed that the expansion of the universe is not slowing, but accelerating, apparently driven by dark energy. This discovery, awarded the 2011 Nobel Prize in Physics, made a perpetual collapse appear unlikely, though some models still allow for dark energy fluctuations that could trigger a reversal. Despite diminished scientific favor, the Big Crunch remains a powerful idea in cosmology and culture. It embodies themes of cycles, rebirth, and cosmic symmetry, inspiring both theoretical exploration and imaginative fiction. Whether or not it awaits us, the concept forces us to confront gravity's ultimate power and the possibility of a universe destined to return to its fiery origins. The Anthropic Principle is a profound idea in cosmology and philosophy, addressing why the universe appears finely tuned to support life. First articulated in modern form by theoretical astrophysicist Brandon Carter in 1973, it challenged the Copernican notion that humanity has no privileged position in the cosmos. Instead, it argues that the universe must be compatible with the existence of observers, because if it were not, no one would be here to notice it. This principle links physics, philosophy, and metaphysics, and has become central to debates about cosmological fine-tuning. At its core, the Anthropic Principle exists in two main versions: the weak Anthropic Principle and the strong Anthropic Principle. The weak form simply states that observers can only exist in regions of the universe where conditions allow life, explaining why physical constants appear just right. The strong form goes further, suggesting the universe's laws are structured in such a way that they necessarily permit the emergence of observers. Scientists such as Robert Dicke, Steven Weinberg, and philosophers like Nick Bostrom expanded these ideas, applying them to problems like the cosmological constant and the apparent coincidences in nature's constants. The implications are striking. The principle provides one explanation for fine-tuning without invoking a designer, instead suggesting that in a vast multiverse, we inevitably find ourselves in a life-permitting universe. It also reshapes debates about whether life adapts to the universe or the universe is tailored for life. Philosophically, it intersects with questions of purpose, existence, and probability. Critics, however, argue the principle is tautological, unfalsifiable, or discourages deeper scientific inquiry. Some dismiss it as a restatement of "we exist because we exist." Others question whether it offers genuine predictions or merely reframes coincidence. Despite its controversies, the Anthropic Principle continues to influence cosmology, inspiring research on multiverses, fine-tuning, and even popular science discussions. Whether it endures as explanation, metaphor, or philosophical puzzle, it ensures humanity remains at the heart of cosmic inquiry. The Ekpyrotic Universe model offers one of the boldest alternatives to the Big Bang, proposing that our cosmos emerged not from a singular beginning, but from a bounce following an earlier contraction. Introduced in 2001 by Justin Curry, Bert Overath, Paul Steinhardt, and Neil Turok, the theory's name draws from the ancient Greek term ekpyrosis, meaning conflagration, echoing the Stoic idea of eternal cycles of cosmic destruction and rebirth. Within cosmology, it stands as a radical attempt to answer a question left unresolved by inflationary Big Bang models. What happened before the beginning? At its core, the Ekpyrotic model suggests that the universe undergoes cycles of contraction and expansion, with the Big Bang reinterpreted as a transition rather than an absolute origin. Early versions relied on string theory and the concept of branes, multidimensional surfaces whose collisions generated cosmic events. More recent formulations employ quantum fields in ordinary spacetime, predicting a smooth, flat universe with cosmic microwave background fluctuations that align with current observations. The implications are striking. Unlike inflationary cosmology, which often leads to the controversial idea of a multiverse, the Ekpyrotic model avoids such outcomes. It portrays the cosmos as inherently ordered, its structure arising from contraction rather than inflation. This framing carries philosophical weight, suggesting that our universe's properties are not random accidents, but results of predictable, cyclic processes. Yet the model faces challenges. Critics argue that Planck's satellite data significantly constrain its parameters, and its mechanisms remain less developed than inflation. The absence of clear evidence for or against cyclic bounces keeps it speculative, and some physicists doubt whether it can fully replace inflationary theory. Despite these debates, the Ekpyrotic Universe continues to inspire research into quantum cosmology and cyclic models. Whether it ultimately supplants inflation, coexists alongside it, or fades into history, it forces us to confront the possibility that the universe's beginning may itself be part of an endless rhythm. The cosmic censorship conjecture is one of the most intriguing puzzles in modern cosmology, directly tied to the nature of singularities and the limits of Einstein's theory of general relativity. Proposed by Roger Penrose in 1969, it asks a fundamental question: are singularities, the infinitely dense points where physics breaks down, always hidden within black holes? Or could they be exposed as naked singularities, visible to the universe? The answer matters because it determines whether physics remains predictable or collapses into chaos. At its core, the conjecture appears in two forms. The weak cosmic censorship hypothesis asserts that singularities formed from gravitational collapse are always hidden behind event horizons, shielding the rest of spacetime from their unpredictable influence. The strong cosmic censorship hypothesis goes further, suggesting that general relativity is generically deterministic, meaning the complete evolution of space-time can always be predicted from initial conditions. In simple terms, cosmic censorship protects the logical consistency of the universe by ensuring singularities cannot interfere with the observable cosmos. The implications are profound. If naked singularities exist, they would undermine determinism and render physics unpredictable, since no laws would govern what emerges from them. By contrast, if censorship holds, black holes remain stable cosmic prisons that preserve causality. The conjecture thus acts as a safeguard for the reliability of general relativity, distinguishing between science and breakdown of order. Still, challenges persist. Mathematical models suggest naked singularities could arise under very specific conditions, such as in certain charged or rotating black holes. Numerical simulations have also hinted at exceptions, raising doubts about whether censorship is universal. In 2018, aspects of the strong version were even disproved in certain theoretical contexts. And despite controversies, the conjecture continues to guide research in relativity, quantum gravity, and black hole physics. Whether it is ultimately proven, refined, or replaced, cosmic censorship remains central to our effort to understand whether the universe is fundamentally orderly or hides unpredictable truths behind horizons. The many worlds interpretation, MWI, of quantum mechanics matters because it radically redefines our understanding of reality, suggesting that every possible outcome of a quantum event actually occurs in separate parallel worlds. First proposed by Hugh Everett in 1957 as the relative state formulation, the idea was later popularized by Bryce DeWitt in the 1970s, who coined the term many worlds. Within the broader field of physics and philosophy, it stands as both a solution to the measurement problem and a bold claim about the nature of existence. At its core, MWI rejects the notion of wave function collapse, asserting that the universal wave function is real and evolves deterministically according to Schrödinger's equation. When a quantum measurement occurs, the universe branches into multiple non-communicating worlds, each realizing one possible outcome. Decoherence, a process where quantum superpositions interact with their environment, provides the mechanism that explains why branches appear classical. Everett, Wheeler, and later David Deutsch advanced this framework, portraying it not as an interpretation but as a literal description of reality. The implications are profound. If true, MWI means that the cosmos is a vast multiverse in which countless versions of ourselves exist, each living out different possible histories. Unlike the Copenhagen interpretation, which relies on probabilistic collapse, MWI is deterministic and removes the need for an observer to define reality. Philosophically, it suggests that events we perceive as chance are simply the branch we occupy. However, criticisms remain sharp. Detractors argue the theory is unfalsifiable since parallel worlds cannot interact. The preferred basis problem once plagued it, though decoherence has addressed many concerns. Others claim it multiplies entities unnecessarily, violating Occam's razor. Despite these challenges, MWI has shaped quantum cosmology, influenced quantum computing, and inspired popular culture. Whether ultimately proven, revised, or discarded, it continues to push the boundaries of how science and philosophy imagine reality. Few concepts feel as fundamental as time, yet many physicists and philosophers argue that it may be nothing more than an illusion. The notion that time is not a basic feature of reality challenges centuries of thought, dating back to Newton's absolute clockwork universe, where time flowed uniformly and independently. This classical vision shaped physics for nearly 2 centuries, until Einstein's theory of relativity dismantled it, replacing absolute time with spacetime, where simultaneity and flow depend on the observer. Since then, the idea that time itself may be emergent rather than fundamental has gained momentum. The central claim of the time as illusion perspective is that physics does not describe a special now or any objective flow from past to future. Equations are time-symmetric, treating past and future equally, while relativity shows that all moments may exist simultaneously in a 4-dimensional block universe. Thinkers such as Ludwig Boltzmann argued that the arrow of time arises not from time itself, but from entropy, the statistical tendency of systems to move from order to disorder. More recently, some quantum gravity approaches suggest that time disappears at the most fundamental level, only re-emerging as an approximate property at larger scales. If true, this idea has radical consequences. It undermines our intuitive sense of living in a flowing present and reframes human existence as part of a timeless structure. Compared to traditional models which assume time as a basic backdrop, this approach suggests that change and causation may be secondary features of deeper laws. Philosophically, it forces us to question memory, free will, and the meaning of becoming. Skeptics argue that denying time contradicts lived experience and risks reducing physics to abstraction. Yet research continues from cosmology to quantum theory. Whether time proves fundamental, emergent, or illusory, grappling with it may be essential for the next revolution in physics. Cosmic consciousness represents one of the most daring attempts to bridge science, spirituality, and philosophy in the study of the human mind and the universe. First articulated in 1901 by Canadian psychiatrist Richard Morris Buck in his book Cosmic Consciousness, a study in the evolution of the human mind, the idea proposed that human awareness evolves in stages, culminating in a higher, universal form of consciousness. Emerging at the turn of the 20th century when psychology and metaphysics were both grappling with questions of mind and reality, the concept offered a radical vision of human potential. At its core, cosmic consciousness is defined as an advanced state of awareness beyond ordinary self-consciousness. Bucke outlined 3 levels: simple consciousness, shared with animals; self-consciousness, unique to humans with reasoning and imagination; and cosmic consciousness, which perceives reality as immaterial, spiritual, and alive. In this state, death appears illusory, existence eternal, and the universe itself is experienced as divine. Influenced by mysticism, religious traditions, and his own transformative experiences, Bucke argued that great figures such as Buddha, Jesus, and Dante may have glimpsed this higher awareness. The implications are profound. If true, cosmic consciousness redefines the universe as fundamentally alive and interconnected, challenging materialist and reductionist views. It suggests human evolution is not only biological but spiritual, moving toward greater unity and insight. Philosophically, it aligns with mystical traditions across cultures, while scientifically it foreshadows modern discussions of consciousness as an emergent or non-local phenomenon. Critics argue the idea is speculative, untestable, and rooted in subjective experience. Neurological explanations such as temporal lobe activity have been suggested as naturalistic alternatives. Scholars also debate whether Bucke confused mystical states with intellectual progress. Yet the legacy endures. The concept influenced psychology, comparative religion, and popular spirituality, inspiring both seekers and scientists. Whether seen as metaphor or reality, cosmic consciousness continues to provoke reflection on humanity's place in the cosmos, leaving open the possibility that human awareness is still evolving towards something greater. Thank you for watching this video. If you enjoyed, please leave a like and subscribe and let me know in the comments if you would like to see more videos like this one. Thanks again. Goodbye.